Hello, and welcome to our talk. Let's see how much varies primary production in the Eastern Tropical Atlantic Ocean in boreal summer, and how when you increase your spatial resolution, you find that the system or some of the systems are more dynamic than we would expect in an open ocean system. So, in boreal summer, we know that there are two active upwelling systems in this region. One is the equatorial upwelling, that we know, of course. When you take a look at the sea surface temperatures in June, July, August, and September, you see that there's a decrease of temperature that starts to develop in June and it strengthens through July and August, and then fades away in September. And it has like a sort of the shape of a tongue, so that is why it is called a cold tongue. So this decrease of temperature is supposed to provide nutrients to the surface that should enhance primary productivity. So when you take a look at satellite imagery, you certainly see this increase of chlorophyll A with this shape of a tongue and a peak in the integrated chlorophyll, monthly integrated chlorophyll in these months of boreal summer. Then we have the Guinea dome. The Guinea dome is a thermal dome, and it has a surface structure that's not evident throughout the year. So we can see here that in December, January, and February is not evident, and it starts to develop in March, April, May, and it's completely developed in June, July, August, and September, October, November. And what it produces is a general uplift or shallow, although isotherms that could maybe get nutrients into surface waters. Though we know this feature from a long time, little is known about the variability of primary production because the few studies that we have come from the 70s and 80s, and most of them are using indirect methods. So what we did was basically going to this region along 23 West, sampling at the highest spatial resolution that we can sample, that we could afford in the late boreal summers of 2015 and 2016. So we did these two cruises that you can see here. The first began in the first week of September, and the second began a week earlier, the last week of August. And we did all these stations and some of the line, but we're going to focus on 23 West, where there are very interesting features. So the difference in the stations between cruises are basically because on the second cruise we decide to increase the horizontal resolution as much as possible, so we focus on surface, as you will see later, and get as many sampling points at surface as we could do. And then we measure primary productivity using the stable isotope method, spiking 13C from in water taken from the water column using a CTD rosette, and incubating on deck, simulating the light. And we basically consider two size fractions, the more than 10 and the 10 to 0.7 micron size fractions of primary producers. Then we also at some station measured the attenuation and quality of light through the photic layer using a spectral radiometer. So the sections of the CTD look like that. You have temperature here at the top, in the middle there's senility, and at the bottom there's fluorescence. And 2015 cruise is on the left, and 2016 cruise is on the right. So you can see in the temperature panels that the structure is relatively similar. You see all this uplift of isotherms in the beginning of the transit in the area of influence of the Guinea dome, and then there's a gradual deepening of the mixed layer that you can see in this yellow line in both cruises towards the equator. There are slight differences, but it's more or less the same. And then in the salinity panels, you see these increases of salinity in depth that can be used for proxying the core of the North Equatorial undercurrent here around 6 north, 5 to 6 north, and the equatorial undercurrent at the equator. So it's interesting that in the region under the influence of the equatorial undercurrent, you see increases of salinity through the photic layer. Then in the lower panels, you see that there's a more or less well-defined DCM at the beginning of the transit in the Guinea dome area, which is very shallow, and then it deepens gradually towards the equator where it seems to shallow again. However, the DCM is not as well defined in this area because in those stations where we see this increased salinity, we also see a high fluorescence through the water column. Lastly, in this panel, you have these cruces. They represent the 1% of PAR, the photosynthetically active radiation. And in general, it was always below the DCM at a variable depth of between 3 and 48 meters. 48 meters in some stations of the Guinea Dome. So it means that the deep chlorophyll maximum was always way above this 1% of PAR. And then lastly, we have these bubbles. Those are the rates that we measure. You can see that, as I was saying before, we have more vertical resolution in the first cruise than in the second because we realized that something was going on and we decided to increase that horizontal resolution. So in general, rates at the Guinea Dome seems to be higher at the equator, and then there's a decrease toward 5 north. But let's see how the surface rates look like to have more clarity. So here you have the distributions of 2015 in red and 2016 in blue, and this upper panel is the rates, and this lower panel is basically the contribution or the smallest size fraction that we had. So as I was saying, the rates are higher. The peak is higher at the Guinea Dome than it is at the equator, and then the peak in 2015 was south of the equator, and the peak in 2016 was more or less centered at the equator, coinciding, if you remember these plots, with this, let's call the shallower position of the DCM. It's not a clear DCM, but it seems to be the shallower position of the DCM, so that's more or less coincident. And then what we can see, and which is more impacting, is that the variability at the Guinea Dome when we increase our spatial resolution is higher than we would expect with a general sampling scheme with 1 or 2 stations a day, when you see these kind of smooth patterns that we saw in our first cruise. So it's that the system is relatively dynamic. Then in general, we see that the small size fraction in the equator is the major contributor to primary production, which is what we would expect in a tropical system, but there's a slightly higher contribution of the larger phytoplanktons at the Guinea Dome in those stations where, you know, all of the sudden production increases. And lastly, so we were saying that the equatorial upwelling, now we're going to focus on the equatorial band. The equatorial upwelling is bringing more nutrients to the surface, which increases productivity relative to other months. So we would expect that these rates are higher than those seen in the literature. So we are using here the Atlantic Meridional Transit Program database from AMT1 to AMT16, the first 16 cruises, and comparing those with our rates. Then we have highlighted AMT3, which was in fall 1996 because it's the closest to our location, and we're going to focus basically on the 6 north to 6 south part of the plot, because as you can see here in the tracks of the cruises, not many of them passed this Guinea Dome region, so it's not really comparable. So you have fall cruises as circles, spring cruises are as triangles, and our cruises. And you can see that in general, our rates are not spectacularly higher than those measured in other seasons. So the question is this equatorial upwelling really bringing more nutrients to the surface, or what kind of nutrients is it bringing? So for summarizing the take-home message, so the Guinea Dome seems to be more productive than the equatorial band. Then the rates around the equator are not extremely high, or not as high as we would expect relative to other seasons. And when you increase your spatial resolution, you see that the systems are more patchy than we would expect in an open ocean system. So thank you for your attention. I hope you enjoyed it.